Hi everyone. In the last video we talked about degrees of freedom, and I think that there may still be some lingering doubts that some people have about degrees of freedom. And in particular, in the last video, remember what we did is we wanted to estimate the population's variance, which we know is the average of the squared distances from the mean, right? So we've got n free random variables, and we're taking the squared distance from the mean, and we're averaging relative to that n, the n free variables that we have, right? And we can't usually do this for an entire population, but we can do it for a sample. And when we do it for a sample, as you saw in the last video, we lose a degree of freedom, because we had this estimate that we had to compute ahead of time. The mean was equal to the sum. In the previous video we had 3 values. And so we got a relationship between the variables, that x3 was really the same as 3x bar minus x1 minus x2. And so instead of having 3 free variables that we're averaging over, we're really only averaging over 2. And so the question that I think people may be having is, why is it that we don't divide by n minus 1 with the population variance? Because it kind of seems like we're going to get that same relation, that if we know that the population mean is equal to the sum of the values divided by n, can't we simply solve for the last variable in terms of the first 4 and reduce the number of free variables that we have? And so to get a sense of why we still have n free variables when we're doing this population calculation, what we're going to do is we're going to do something completely unrelated to population variance. And we're going to look at a variance relative to some arbitrary value a, okay? So here's the value a, and just like in the previous video, we're going to think of the real number line as being down here. So this is where our numbers are bouncing around, but then we're going to use the space above it to describe the points so that we can have a little more space to describe this, right? So we have a fixed but arbitrary value a, and so here's that a value, and let's consider an entire population. So we got, maybe there's 5 points randomly distributed along this number line, okay? And let's suppose that we want to calculate the average squared distance to a, all right? So what we would do is we would take these distances and we would square the distances and we would average how many there were, right? So let's just call it a. So the average square distance from the value a says take the values minus the a squared divided by how many there were. And these things are all completely free to vary, right? There's absolutely no relation to a whatsoever. A is just an arbitrary fixed number, so these 5 points can be wherever they want. That determines some distance to the mean, and that determines these squared distances. So when we take the average squared, not distance to the mean, average squared distance to a. So when we take this average, indeed, all 5 of those are completely random, and there's no relation between those points whatsoever, right? And so, just like in the last video, we don't usually have an entire population, we usually just have a sample, right? So let's suppose that instead of having all 5 of these population values, suppose that we only knew of 3. If we only know of 3, and suppose that we don't know exactly where a lives, if we only know of these 3 points, and we want to estimate where a lives, then we have to cook up some function, right? So there's going to be a function of these. We're going to say, take x1, x2, x3. That's going to give us some estimate of where a lives, okay? And so let's call it a bar, okay? And so we don't know exactly where a lives, but we can sort of cook up some function where we take a sample of values, and it'll be close to the original a, but just a little bit off. So this is our A bar, right? And so this is sort of the key idea, is that whenever you estimate a parameter, you're introducing an equation that relates the random variables that you had in a relationship that basically decreases the amount of flexibility that you have, right? Because this A is going to be determined. Once that A is determined, then you could vary x1, you could vary x2, but x3, you could solve this equation in terms of x1 and x2. And so you could solve this, let's call it G, and you'd get this fixed relationship here, that G of x1, x2, and that estimate A bar gives you x3, okay? So this is sort of the key idea, is that the minute that you use a sample to estimate a population parameter, what happens is the equation that you get, you can solve for one of the variables in terms of other random variables. And so this x3, once you know x1 and x2, x3 is now determined, right? And so the basic idea, the subtle difference between computing a population value, like we did here, versus computing a sample value, is that when you compute a population value, this thing is fixed, and you could essentially think of it as like an arbitrary value, where it's just a fixed value that has, in some ways, no relation to the underlying random points. And so you really do have 5 free variables that you can compute. What happens though is that once you start trying to estimate this, there you lose your degree of freedom because you introduce a relationship between the variables, okay? And so that's the difference that I wanted to talk about. So